Hello students, this is Dr. Anita Raj, your chemistry mentor, welcoming you for a new session in transition and inner transition elements, that is D and F block. Today in this session we shall see a new topic and a very important topic, that is lanthanoid contraction. Okay. So before going into the topic, that is lanthanoid contraction, first you should know what are lanthanoids, that is lanthanoid series, right? See, the lanthanoid series is also known as the first series of rare earths or first inner transition series. See, these are the lanthanoids, okay? It starts from lanthanum and it ends at lutetium, right? So, these are called the lanthanide series. Actually, this series is characterized by filling of electrons in the 4f orbitals in the atoms and consists of 14 elements from cerium to lutetium. So, I have given the names of those elements. It starts from lanthanum, cerium, and it goes till lutetium, right? Here the atomic number increases and subsequently the electrons will be filled in the 4f orbitals. Just check the electronic configuration from cerium to lutetium. See here, here we have 4f1. Next, see here from cerium to lutetium, the successive electrons are added up to the 4f orbitals, is it not? And these elements, they strongly resemble a lanthanum in physical and chemical properties. That's why these elements are called as lanthanoids, okay? Now we shall see what is a lanthanoid contraction, right? So lanthanoid contraction. See, lanthanide contraction, otherwise called as lanthanoid contraction, is the steady decrease in the size of the atoms and ions of the rare earth elements with increase in atomic number from lanthanum to lutetium. Can you understand? There will be a steady decrease in the atomic size or the ions of these rare earths, though there is increase in the atomic number. Okay. See here, this is lanthanum. Okay. So, lanthanide contraction, there will be a steady decrease in the size of the atoms, okay, when it moves from lanthanum till lutetium, right? So, this is called as a lanthanoid contraction, okay. So, it has been observed from moving from cerium to lutetium, the size of the atoms or the ions decreases regularly. And this decrease in size is more regular in the case of the tripositive ions, okay. See here, lanthanum tripositive and cerium tripositive, promethium tripositive, okay. See here, when a graph is plotted between the ionic radii of these tripositive ions with that of their atomic numbers, we could see a gradual decrease in the graph, okay. The ionic radii is gradually decreasing, though the atomic number is increasing, okay. What is, see, this is called as lanthanoid contraction. But what could be the reason for this lanthanoid contraction? Let's see the reason now. The reason for lanthanoid contraction, actually the main reason is when you move from cerium to lutetium, the nuclear charge increases with atomic number and the differentiating electrons are added up in the inner 4f orbitals, okay. So, they are added up in the 4f orbitals, right. So, the successive electrons are added up in the 4f orbitals. And the main reason here is the lanthanoid contraction is the result of poor shielding effect of the 4f electrons. Understood? What do you mean by shielding effect? The shielding effect is a phenomenon by which the inner shell electrons shield the outer shell electrons. The inner shell electrons shield the outer shell electrons from the nuclear charge. Okay, they shield, and so that the nuclear charge will not affect the outer shell electrons. Understood? See here, in the case of cerium, from cerium to lutetium, the nuclear charge increases, okay, with atomic number, and the differentiating electrons are added up in the inner 4f orbitals, okay. The nuclear charges will be going on increasing from cerium to lutetium. Likewise, the electrons will also be increasing, but the electrons will be getting added up to the same subshells, right? So, same 4f orbital, okay. So, in this case, what happens is the electrons which are present in the inner 4f orbit, they will be showing a poor shielding effect for the 4f electrons. So that what happens, the nuclear charge will be having a direct attraction on the 4f orbital electrons, okay. Since it is pulling the electrons towards itself, automatically the size of the atom decreases, okay. The size shrinks, okay. These electrons will be pulled towards the nuclear charge. Therefore, with increase in the atomic number, the effective nuclear charge experienced by each 4f electrons increases. This causes a slight reduction in the size with addition of each electron in 4f subshells. Can you understand? Thus, with the addition of each electron in 4f subshell, there is a steady increase in the effective nuclear charge, resulting resulting in the steady contraction in the size of the atom. Can you understand? So the successive contractions gets accumulated and the total effect for all the lanthanoids is termed as the lanthanoid contraction. From starting from cerium to lutetium, the total contraction is about 15 picometer, right? So that's why the size is getting reduced, okay? And this is called as a lanthanoid contraction. Understood? Now we are going to see the consequences of lanthanoid contraction. The first one is the atomic radii and ionic radii. Let us see what's going to happen for the atomic radii and ionic radii due to lanthanoid contraction. Okay. See, in the case of group 3, the atomic radii increases regularly from scandium to lanthanum. Is it not? It is increasing regularly, that is 164, next 180, okay, and likewise it is 187, right? So likewise it is gradually increasing, but this trend disappears in the following groups, okay? We cannot see a gradual increase. See here, it's from here it is decreasing, 159 to 156, it is decreasing. Here almost the similar, here little increase, here a little more increase, is it not? So this is not the same as that of group 3. There is the trend disappears in all the following groups due to lanthanoid contraction. See, when you take into account the pair of elements like zirconium and hafnium, niobium and tantalum, then molybdenum and tungsten, and also this palladium, platinum, silver, gold, and then rhodium, iridium, we could see almost the same value of atomic radii. Is it not? Say almost the same value of atomic radii. But the atomic radii of hafnium and tantalum, okay, hafnium, tantalum, tungsten, etc., would have been much greater as compared to that of zirconium and niobium and this molybdenum. But this occurrence of this lanthanide contraction cancels the expected increase in the atomic radii values from hafnium to mercury. Can you understand? Since the element pairs zirconium, hafnium, niobium, tantalum, etc., these elements, they possess almost identical atomic radii. So they are very difficult to separate because solubilities of these salts are very close. Can you understand? Next important property is density. Actually, a reduction in the size of atoms due to lanthanoid contraction increases the densities of all the elements placed after lanthanoids abnormally. Okay, so let us see here. See, in group 3, the density increases very regularly from scandium to lanthanum. Is it not? It is regularly increasing. 3, 4.5, then 6.2. Okay, but in the case of group 4 and subsequent other groups, the densities of the third row, this is the third row and this is second row. Okay, this is the first row. So the densities of the third row elements are almost double to those of corresponding to the second. See here, it is almost double, is it not? So the values of densities are almost this double. Okay, so this abnormal increase in the densities of the elements of third transition series is solely due to lanthanoid contraction. Can you understand? So ionization potential, see, the phenomenon of lanthanide contraction also affects the values of ionization potential of the elements of third transition series from tungsten onwards. Okay, so in the absence of this lanthanide contraction, these values should have been much lower and should have decreased regularly on descending the group. Can you understand? Next important consequence is the basicity of oxides and hydroxides. See, due to lanthanide contraction, the basic strength of oxides and hydroxides of lanthanides decreases with increase in atomic number. So the basicity is decreasing. See here, lanthanum hydroxide is most basic while lutetium hydroxide is least basic. What's the reason behind that? The accumulating lanthanoid contraction goes on decreasing the size of the lanthanoid cations. Okay, so it will be decreasing the size of the cations. When you move from lanthanum to lutetium, the size of the cations will be decreasing. Okay, therefore, with the increase in the atomic number, the polarizing power of the lanthanoid cations also will be increasing. This results in a regular decrease in the ionic character of these oxides. Okay, the ionic character of the oxides will be decreasing and the cationic character will be increasing for the oxides and the hydroxides of this lanthanoids. Okay, and they become less and less basic. Well, fine students, I hope you might have understood what I have taught today. Let me meet you with another important topic in my next session. Until then, it's Dr. Anita Raj, your chemistry mentor, signing off from you. Thanks for watching.